To today's session. We're going to talk about CXL. MemVerge, we have presented before. We are a big memory company, and CXL is one of the most exciting memory technology that come to the market in the last 20 years. And we're going to tell you all about it. We have invited our hardware friends to show you what they got in the hardware that's coming to market. And we're going to have Steve to tell you everything that we can do from software perspective. So it'll be an exciting 2 hours. So first, let me share the motivation and some basics 101s about CXL. So obviously, we all know in the last 10 years, the applications are becoming increasingly data-centric and data-intensive, from AI to EDA simulations to computational fluid dynamics. And if you're like me, we have been playing with ChatGPT over the last couple of months. And it certainly uses a lot of memory. So it's a large language model that has billions and billions of parameters, and all of them need to sit in memory. So all this is driving more data. We are seeing a lot of data growth over the last 10 years, and in turn, that more data is driving more memory. With all these applications, if the data can fit in memory, it stays in memory. You don't want to go to storage, and there's a name for it, that's called spilling. So whenever the data spills out of memory, that's not good news. The application goes down, and so there's need for a scalable and composable approach to memory so that you can always have enough memory for the data that needs to stay there. And that's really the fundamental motivation for CXL. And it manifests itself in two ways. One is the bandwidth. The memory bandwidth is increasingly a bottleneck for the applications. Over the last 10 years, we are seeing this divide to widen between the kind of core increase and the per core bandwidth increase. So in fact, the orange bar is the okay, I think the label is reversed. The orange bar is actually the bandwidth per CPU core. Over the last 10 years, it's actually been decreasing rather than increasing. So whenever that becomes a bottleneck, they typically refer to it as running to a memory wall. And this is common in many applications, especially AI. A memory wall is a very common term among the AI workload. And that's why they have high bandwidth memory. They have various ways to increase the bandwidth that for data computing nodes and the memory. And this is one of the things CXL can improve because it runs on PCIe Gen 5 and later, and it essentially add that bandwidth to the DDR bandwidth that's already there, connecting to the DDR memory. It can potentially increase memory bandwidth by 3x or 4x. And that will alleviate this memory wall problem. The second the bottleneck is the capacity of memory. The models are becoming bigger. We are seeing here showing 100 billion, 1 trillion models. As we are talking about ChatGPT, it has 175 billion parameters in the model. The next version of it, GPT-4, there are various speculations to as high as 100 trillion parameters. So that's going to use 3 orders more memory than what's available today. And whenever it doesn't fit in the memory, you either need to increase the number of nodes to have more memory space, or you need to go to storage, which is orders of magnitude slower. So this becomes a bottleneck, and we need a bigger memory solution, and we need this memory to be hopefully dynamically scalable so that whenever you need it, you can have it. Whenever you have a distributed application, one common problem, you cannot predict how much memory each of the node needs. And there's a problem called skewing that results, meaning some of the node will need more, some of the node need less. And so you cannot pre-allocate the right amount of memory to each of the node. You need to dynamically respond to the application needs. So you need to have a way to dynamically provision memory to the node that's needed. And this is what CXL can solve. So this is kind of my picture, which is a little different from other picture you see that drawing the CXL. The circle is the CXL bus. And this is fundamentally a disaggregation between the memory that's connected to CXL and the compute that's connected to CXL. So you can have various processors from CPUs to GPUs to AI accelerators to TPUs to DPUs, whatever processor you have connecting to the CXL bus. You can also have various type of memory connected to the CXL bus. You can have DRAM, you can have new memory types, you can have even NAND flash connected to CXL as well. And any processors can talk to any of the memory, and this disaggregates between compute and memory, meaning each of them can scale independently. And that solves a big problem because memory is really the last resource in a data center that is not disaggregated and that cannot be scaled independently. Like today, memory is sort of directly connected to each socket. So that's why if you go to Amazon or you go to any of the cloud, each instance is configured with a certain ratio between the number of cores and the amount of memory. You couldn't really dynamically configure how many cores, how many memory, because they are more tightly coupled. With CXL, it decouples this, meaning you can choose any ratio between computing cores and memory sizes and to fit the workload that you need. So the benefit, you break through the memory wall, you avoid the I/O wall by having the memory capacity, and you disaggregate memory from compute so that the entire data center can now become composable. Before, the storage, networking, even GPUs can be made composable. Memory is difficult. Now memory can do that too with CXL. Okay, and let me just share another perspective that, given that I have personally worked in the storage field for 20 years before we started MemVerge, we see a very interesting analogy of what CXL could do to memory that's similar to what storage networking did to storage 30 years ago. Back in the early 90s, storage was just a component of a computer. So there was no such thing as a storage array or storage networking. You basically buy a computer and configure how much storage it has. But then there emerges fiber channel, and that basically disaggregates storage from compute. And therefore, there becomes available your storage area network and SAN arrays. You can have your logical volumes that can be dynamically provisioned to any of the hosts that's connected to the pool. There emerges storage software, storage systems, and the entire industry was born out of it because that disaggregation, the storage become its own being. And there are companies like Veritas, EMC, NetApp, Pure Storage, etc., all emerged because of this disaggregation that happened. And similar here, today, memory is not its own being. It is part of a computer. When you buy a computer, you configure how much memory you need, although it's a pretty expensive part of a computer, but it's still part of a computer. But because of CXL, we think there could emerge an independent memory product. And there could be independent memory software, memory systems that runs on a memory fabric, which is CXL today. And there could be a new industry that come out of it. And there could be new technology and new company that was created, just like what happened to storage 30 years ago. So we see a kind of a parallel of what could be happening in memory space in the next 10 years to what happened in storage space from the early 90s to the 2000s, that essentially $100 billion market was born out of nothing because of this disaggregation that happened. And the benefit it can bring are the scalability, manageability, and the various data services you can enable through software that's on this disaggregated tier of storage before, now memory now. So now just some basics about CXL. There are 3 types of CXL devices that are coming out. They call it Type 1, Type 2, and Type 3. Type 1 are essentially more for the computing side, the accelerators. Type 3 are more for the memory side. These are memory expansion cards. And then there are Type 2, that's kind of combination of Type 1 and Type 3. And I think our friend from Astera Lab will hopefully show you a Type 3 card in about 20 minutes here. So these are the new hardware devices that are coming to market. And they are largely based on today CXL version 1.1 definition that came out in 2015. Oh, sorry, 2019 is when CXL version 1.1 spec came out. And that was mostly designed for memory expansion, where you can insert a new device to a host to increase the memory capacity and bandwidth it has. And 2.0 was published a couple years ago, and that essentially allow you to have a switch that can connect a number of hosts to a number of memory devices, and you can dynamically provision the memory to any of the hosts. So this is really kind of, you have a memory network now, and our friend from XCON will show you what they are doing in bringing this switch to life. So this is essentially a PCIe Gen 5 switch that can run CXL protocols on top. You can connect any of the memory modules to any of the hosts to dynamically increase or decrease the memory capacity available to that host. And then there's a CXL 3.0 that just came out last year as a spec. And this essentially allows at least two important features, more than two, but I'm just going to introduce two of the features. One is it allows a cascading of switches. With 2.0, it allows the devices and hosts to connect to a single switch. With 3.0, you can have switch, connect to switches, increase the scalability and fan out of this memory network. And then it also have a specification for cache coherence between the hosts for memory sharing, which in my analogy to storage is kind of the NAS, the network touch storage equivalent, where you can have multiple hosts access the same memory region at the same time. And it can ensure the cache coherence of that kind of a multi-access. And that is really the holy grail in some sense that we have been hoping for the last 20, 30 years. Now it allows an application to expand to multiple hosts while they can continue to have access to the same memory. They can dramatically change the way how distributed applications can be designed. And similar to when you have a shared storage, you can design certain applications certain ways. When you have shared memory, it can open up a big stage of new type of application that can come out. And I'll go into some of the use cases in a second.
Quick question about the hardware of the switches. I don't know if you're going to see more in detail, but I'm just thinking if I take PCI Express lanes,
yeah,
and now I have a switch, what backplane does the switch have to be able to sustain that throughput that comes with CXL3?
Yes. So indeed, XCON JP will go into more details, and he will introduce into their switch, which the fundamental thing is this chip, this controller chip that can manage that high throughput. Essentially, their switch going to support 16 port, and each of them is a 16 lane. So it's a total of 256 lane, and they have a backplane that switch that can support that 256 times. You know, if you count both ways, it's about 8 gigabytes per lane. So it adds up to 2 terabytes of a backplane that switch will support.
That is impressive.
Yes, and it is impressive. So. Okay, so that's the basics of CXL 1.1, 2.0, and 3.0. All right, so and then in terms of the market size, we are start seeing some estimates from analysts like Gartner's, and this is a Gartner report that's estimating that we're gonna reach about 2,000 petabytes of CXL connected memory by 2028. And that basically reached to about 8.5% of the total memory going to be CXL connected. So there are other analysts give more aggressive or optimistic forecasts, but even this is a significant amount of memory in the next 5 years that's going to be connected over CXL. So it is happening, and revenue-wise, it's forecasting in the same time frame for the CXL memory to reach $3.5 billion market size. So this is just one of the analysts predicting the market size here. Now, let me go into the use cases. So now we have this wonderful technology. So what can we use it for? And that's a question I think us and our partners really have been trying to figuring out. This is clearly a groundbreaking architecture. This is clearly a wonderful technology with the new controllers, the new switches, and all those coming out. But why do we need it? So now I'm going to go into 5 or 6 different scenarios that we have discovered over the course of the last couple of years of how CXL memory could be utilized, either to reduce cost or increase performance or increase manageability or basically allow people to do things that wasn't possible before. And let me go into each of them. And then I'll hand up to Ahmad and Steve and JP to share with you exactly how that's going to be done. So the first use case is about stranded memory. And this is particularly important for hyperscalers or anyone who has a sizable data center. There's a paper that was published last year by the Azure team, and they actually have a new paper that's updated this called Pound that's coming out in a couple of weeks in a conference, that they did a survey of the Microsoft Azure data centers, and they have found that about 50% of the cost of that servers in that data center are memory cost. So memory is becoming a significant cost factor for their data centers. And then what they also found is that about 25% of their memory is stranded. What they mean by stranded is that that memory is not being touched at all. It's not being allocated to any virtual machines or any containers and not used, just sitting there, unutilized. The reason they have that is because in order to answer to the demand, they have to have enough memory in each of the server box. And because it's no CXL, not dynamic configurable, they have to kind of max out the server memory size. And not all servers gets fully utilized, so there will be a lot of memory sitting unused there. And then of the 75% of memory which actually gets touched, they found so those memories are being allocated to the virtual machines. But they found over 50% of VM never touch more than 50% of their memory. So they call it frigid memory. So that's also, if you calculate that, that's more than 25% of memory that's unused, even after it's signed. So overall, really less than half of the memory is being utilized. More than half of the memory is not being utilized. So they're trying to figure out how to solve this problem, and CXL come into play. So once you have a CXL pool of memory, that now allows you to reduce the amount of memory you provision for each of the server, and because you can dynamically add memory when it's needed. And when you have a memory there, you can even, as I talked about next time, you can do the actual provision or you can do thin provisioning. So there are various ways to increase utilization of memory and therefore achieve significant TCO to hundreds of millions of dollars or billions of dollars, depending on the size of a data center. So this is a dramatic TCO improvement by decouple the memory from servers and allowing dynamic provisioning of the memory resources to increase the utilization of your memory resources and reduce your total cost. All right. So now a sort of a similar use case to that is even without a huge data center, that we can enable a thin provisioning capability through CXL. And this is quite similar to a SAN thin provisioning case, that as we allocate memory to the servers, we don't have to physically allocate the entire quantity of memory to the servers. You can say, I give you 512 gigabytes to the servers, but only give you 128 to start. And once you getting close to that 128, I'll give you another 128. So it's similar, say, to a bank. When they say they have $1 billion, they only have $200 million. The bet is not all of us need to get the money at the same time. So having this thin provisioning way, you can essentially promise more than what you actually have, and hopefully always be able to meet that demand. So next one is an interesting one for fault tolerance purposes. So memory does go bad, as we know, and now people have built protections on the memory controllers with error correcting code and so on. So when you have a small number of errors, it's okay. They can deal with it. But as the error number goes up, it's going to reach the limit of that ECC code, and then the entire module would go bad. And when the module go bad, it can have bad effects to the applications that's running on that particular server. And from memory vendor point of view, they can actually know when the error rates start to go higher. Now with the CXL memory available, even if the entire memory on that server node is being used, if some of the modules, the error rates start to go higher, then we can actually dynamically provision memory from the pool and through software perform some transparent migration of the data from that declining memory modules to the new memory modules without impacting the applications, and then activate the new module and deactivate the old module after this transfer is complete, all without changing the application. So you can have essentially an auto-healing process of your memory to protect against the memory module failures.
Is it hot swappable, or does the memory module stay in there until you have a maintenance cycle? Or
so after this memory goes down, it depends on the operating system support. I think if not now, over time, I'm sure it's going to enable the hot swappable of the memory modules. Yeah, it probably will depend on the OS levels and BIOS support. All right, so that's the previous three use cases were kind of memory pooling use cases. As long as you can dynamically add memory to each servers, you can do that. Now I'm going to go into even more interesting memory sharing use cases, where if multiple hosts can share memory, there are more powerful features that can be built. So first is a distributed database caching. The modern databases, especially the cloud databases, increasingly distributed. They'll have multiple worker node or multiple execution engine that are doing those queries. And the data often sits on some storage services like S3 and so on. But S3 is slow, as we know. And so each of the worker node typically have a cache. And this is a memory placement of data so that it can provide fast speed and for each of the nodes to process. And these cache tends to be local to each of the worker nodes. Now, if you have multiple worker nodes, number one, each of them need a cache, so you need a lot of memory to do that. Number two, if node A has it in the cache, node B doesn't have it in the cache, then node B need to load in the cache. So it's not optimizing performance because each of the cache are independent. And once the data is updated, there are also more cache units you need to update. So that is a very expensive and complex process where you need to kind of invalidate the cache across all these caches and update them all. Now with CXL memory, it's possible to have a shared memory cache to each of these worker nodes. So once you have a shared memory cache, it solves all these problems. Now, if the object is in the cache already from node A access, node B can enjoy that cache as well. The total amount of memory needed is less, and you don't need to coordinate among all these independent caches. So it can provide a much better cache for a distributed database application.
Does CXL have some capability to do atomic operations on the memory?
I think it's going to be similar to the DDR memory. So it's cache line. So each cache line access is atomic.
Okay, because
but in terms of database transactions, from a memory level, it doesn't do that. It requires the application. So if you're talking about the base access, it has a cache line atomicity. If you're talking about the database transaction atomicness, that needs to be managed by the application itself. So the memory itself just behaves like a DDR.
Well, if you actually have separate compute nodes, how do you actually synchronize that then?
Right.
I mean, you need some sort of atomic primitive in CXL.
So that's a great question. So with CXL 3.0, if there's a hardware that fully support the 3.0 spec, including the cache coherence, that hardware module will manage the locking between the multi-hosts if they're accessing the same memory region, so making sure the access is consistent. So that's going to take a few years. And before that's available, Steve will go into the offerings that MemVerge does. We are actually creating a software implementation on top of CXL 2.0 that can enable cache coherence through software. So enable the atomic access, ensure they don't step on each other's toes, and we have consistent access to the data. And that's one of the key and perhaps the most exciting software technology we are bringing out.
Okay, great.
Yeah. Okay, now we are talking about databases. Those are relational databases, but not only databases, but also other type of data processing frameworks like Spark, like Ray, like various big data or AI, ML type of frameworks. They also can benefit from a shared memory implementation. One particular example is for data shuffling. So data shuffling is what happens, say, in a sort of a MapReduce like workload. You would compute on all these nodes, and then you will need to shuffle the data between those two nodes, and for the next stage to happen. And all these shuffling today occurs over network, meaning it's actually a physical copy of the data. You need to serialize and deserialize it, and it's time consuming. And often a job could take more time in doing shuffling than doing the computation itself. So it's a time-consuming process of big data processing, and that's because it's placing storage, go over a network, and doing all of that. And with shared memory, essentially it create a new mechanism where all these data can be placed in shared memory. All of them will have access to it, and you basically eliminate this shuffling process. You can do now these computations without actually shuffling data, incurring all those data copying and serialization and deserialization, and dramatically improve the performance of these type of workloads. And then I think I touched on this before. This is particularly true for sort of AI type of workload. They also have multiple worker nodes, and they have the cases where the spilling happens. So some of the memory nodes might outgrow the memory, and it going to storage that slow down the application. Where if we have dynamic CXL memory, can add memory to that node, keep it in memory, therefore it doesn't slow down. And we can also enable. So that was just using data pooling. With memory sharing, we can allow a zero copy data sharing between them as well, achieve similar benefits as we showed in the shuffling case. So with all of these worker nodes, they can have access to the same shared memory, therefore have access to all those data, saving the copying that's needed. So therefore they achieve zero copy data sharing. So these are wonderful, interesting new use cases, and it requires an entire ecosystem to collaborate to bring these solutions to market. I think 2023 is a important year. It's like year zero of CXL technology. The theme of this talk is CXL is ready to take off. And this year, we are going to see the first hardware product hitting the market. I think we're listing some of this here. Among the processors, new Sapphire Rapids and Genoa and new ARM platform are claiming support for CXL 1.1 and 2.0. We are seeing the first generation of controllers, including Astera Labs, which is going to present next. And we are seeing even the first switch chips starting to come into market. And the hyperscalers are looking into it. The system vendors starting looking into it. And I think software guys are starting to look into it as we are. So it takes a village of ecosystem partners to bring CXL technology to market to solve answer to those use cases. And in the follow-on sessions, we're going to have our hardware partner, Astera Labs and XCOM, to share their exciting plan on their hardware. And then Steve is going to dive into the software offerings that we have.
Yeah. You mentioned a really interesting point there around the serialization of access to memory. And we keep going back to storage references here.
Yes.
It's like when we went from parallel ATA to SATA.
Yeah.
or SAS. And through a recent CXL podcast, I learned that PCI Express lanes only require a third of the CPU pins
Mm-hmm.
on
Yes.
the actual processor.
Yes.
So it just seems like a much more scalable way to add more input-output bandwidth to processors over time here. If we can reduce the amount of traditional memory channels and increase on CXL, that'll again help with achieving more bandwidth coming through with the additional potential PCI Express lanes, because we're starting to hit some limits here on how many pins we can actually put
Yes. Yeah.
on a processor.
Yes, that's a great point that I should have mentioned. I think the memory wall problem is essentially the bandwidth limitation between CPU and memory, and so the efficient utilization of CPU pins become important because that's a precious assets of those pins. They only have so many, and one benefit of CXL, which runs on PCIe, is that it's 3 times more efficient in using that ping. For each ping, it can get 3 times more data through compared to DDR, regular main memory access. So that's one of the benefits CXL brings in terms of alleviating that memory wall problem.